Hello, welcome to Tech Talk with Steve. I'm your host, Steve Cowles, product manager with AEM. Welcome to episode number 29, ensuring shield integrity in field testing. So we're going to be talking about shielded cabling today and how you will be using your test equipment to ensure that that shield not only has continuity, which a basic wire map will tell you, but that the shield has integrity throughout, which is going to be important. I'd like to welcome to the show Harshang Pandya. He is our general manager. He's got extensive experience in leading the development of electronic test and measurement systems. He joined AEM in 2017 as general manager, and he was part of an acquisition of a company called Inspirain, a Singapore-based company that he co-founded. Before founding that company, he's had over 20 years of experience in managing full life cycle of test and measurement equipment. He's got a Master's of Technology degree from IIT in Mumbai. He attained that in 1994. And in his spare time, Harshang likes to enjoy exploring nature and playing board games. Welcome, Harshang.
Hello, Steve. Thank you.
Good to have you here. So shielded cabling, there's a lot of, in Europe, it's used extensively. Here in the US, not so much. But there sometimes seems to be a little bit of mystery about shielding. But some of the benefits of shielded cabling obviously are the noise. You help to reduce the noise that's getting into the cable as well as the noise escaping the cable and causing something we call alien crosstalk in an installed environment where you've got bundles of cable together. But it's really important when they install this cabling that it's not only terminated properly, but the shield on the installed cabling is bonded properly at the patch panel end, which is then in turn bonded to the building ground system, and then at the wall plate end, it has to be terminated in a shielded jack, which then gets grounded by the patch cord going to the equipment at that endpoint, so that you've got it grounded at both ends essentially to help keep that noise from getting into the system. So when it's installed, it's important as part of the installation, not only just to show the continuity of the shield, but also to be sure that beyond the continuity of the shield, that shield is the same throughout, that you don't have some anomalies in the shield that are going to cause problems. Is that a fair assessment?
Oh, indeed, Steve. So as you rightly said, the shield is actually for protecting the noise from getting out of the cable and external noise from entering the cable. And in fact, that is the interesting part of the shield. It does not play an active role in the normal transmission. It just protects the noise from coming in and out. And so if there are issues in shield, it becomes kind of challenging to find those issues, because with normal transmission, you may not clearly see the issues that exist until when the cable is hit by some external noise. Right. So that's the interesting part of the shield.
Gotcha. So I'm going to share my screen here just to show a couple of things. So what I'm going to do is I'm going to back out of this. I want to plug into an installed cable here. And in this case, what we see is there's a wire map. So the wire map looks good. It shows continuity on my shield. And so isn't that enough? Doesn't that tell me that, yeah, this cable's good and my shield's good, I should be ready to go?
Yeah. In the beginning, yes.
In the beginning, yeah. So we've got continuity. So a simple wire map tester will tell you this. Now, if I run an auto test on this, and I've got this set up as testing a shielded cable, we can not only test it for whatever test limit we're running, but we're going to test the shield. So we look at the wire map. Now we see we've got some issues here on this shield. It's showing us some anomalies in the shield. And if I look at my shield locator, I can now see that I've got an open on this shield. So I've got an issue with this shield. Now in the case here, I've got a shielded patch panel here, but I don't really have shielded cabling behind it. So we're seeing an anomaly here in the patch panel where it's looking like it's got continuity, but it doesn't. This could also occur in a situation where you've got a a data center where maybe you've got patch panels at both ends of a link, and you've got, because the patch panels are shielded, when you plug jacks in, next to another one that's shielded, you've got that bond going, through that panel. But at one end or the other, you may not have that bond in place, and you can show that with a graph like this, correct?
Yes. So, Steve, your setup is also somewhat similar to what you just described.
Right, except that it's an unshielded cable I've got in here. So, so what we're seeing here, we can see an open, and I've got another example of another open that we can look at here, so that the viewers can take a look at this, and we can show a cable with an open like that. And in this case, we'll see we've got an open. We can clearly see at both ends where we see this spike in that TDR trace, the shield TDR trace here, where we can see an open. And if we click on that spike, we can see how far out it is. And that's right out at the end of my cord from my permanent link adapter. So I know that there's a shield change taking place right there. And we can, because this spike goes all the way up, that means that it's telling us that the shield's open across this distance, correct?
Correct. So Steve, in TestPro TDR traces, I mean, this is a unique thing about TestPro with the shield locator, and it shows two types of TDRs. The one you see at the bottom, that is the impulse response TDR, where you see whenever there is a transition, you can see those spikes that you were just showing.
Right.
And the one on top, the two curves, are the step response TDR, as they are called. And there are two plots. So the one plot is taken from the main device, and the other plot is from the remote device. Right. The interesting thing about step response TDR is that it shows the impedance of the cable at every point in time, every point in the distance. So if you put your cursor at any point and you see the value there, that is the impedance of the shield right there. And it becomes a bit technical, but I go back to our earlier discussion that the shield only plays a protective role. So if you are sending differential signal on the cable, which is what the cable is designed for, right? The twisted pair cable is supposed to take differential signal from the transmitter to the receiver. And in that differential signal transmission, shield actually does not play a very active role. What it also means is that if you want to locate these kinds of issues with shield, if you are sending normal data like differential transmission, it would not be possible to do so. So the test equipment purposely sends so-called common mode signal, which is basically somewhat like treating the two wires of a pair as one wire. We send the same signal on both wires at the same time. So it basically, the twisted pair cable then kind of becomes like a coax cable, because both conductors carry the same signal, right? And by doing so, we can now see the shield playing an active role in the transmission path, and that helps in determining shield faults. So it is quite complex to find this kind of issues, but by using the so-called common mode return loss and the time domain response of that, we are able to show these issues. And this is very useful because you can see even sometimes you see that there are no faults in the shield, but the cable changes from an FTP cable, which is only the outer foil, into an STP cable where you have shield in every pair and then you have outer foil. So if you have those kinds of transitions in the cable, you also can see those transitions, right? Because the impedance changes with every transition in the shield. So
and that's the example we're seeing here, right? Where, and we'll notice this impedance is a much lower value. The other one was up around, I want to say 40 or above, but this is a lower value. So in this case, we're seeing some spikes here, but what we're seeing is a change in the shield type. Is that correct?
Change in the shield type, exactly.
Okay.
Right, and it is very important to see such transitions because Steve, I think you have been telling before that the cable is only as good as the weakest part of the link, and right. So if you have like a one poor quality cord or a unshielded cord, and because of the bonding, the wire map doesn't detect it because DC continuity is present. But if you have such component in the middle, it is like having the whole cable as unshielded. So all the effort in shielding is wasted just because of one component that mistakenly comes in, right? So by looking at this exact location of where that component is and what is the nature of that, it helps in not getting into that trap, basically.
Gotcha. Now I've got another example here, and I just need to make a quick change because I think this one will be something interesting for you to talk about. So I'm actually going to change this adapter on my remote end, and yeah, it's not considered kosher to run a permanent link test using a channel adapter on the remote and a permanent link on the main. That's not what we're suggesting here. I'm just doing it for the convenience of running this test. And I've got the other end of this cable. It's a shielded cable. I'm going to put a coupler on here, and I'm going to take my cord from my permanent link adapter and connect to this. And let's hit my home button, and I'll plug in, and I immediately get a wire map. Shield looks good. Wire map, says the shield is good. So I'm going to run a test on this, and we'll see what happens. In this case, we failed. We've got other issues here too, but so I'm going to look at wire map, and here we see we've got an issue with our shield. But if I go to the details and look at my shield locator, here I've got a big spike in the middle of my cable. And in this case, what we've got, this shield is it's open at the midpoint on this cable, but there's just a little bit of the shield still connecting. So it's a case where the shield, the cable jacket got compromised. Maybe a rodent, for example, in the real world, chewed the jacketing of the cable, compromised most of the shield, but left just a little bit, maybe just a little tiny bit of braid or a little bit of drain wire is making contact between the two pieces of the shield, and that's what we're seeing here. So this is something that can easily be identified with TestPro as well, right?
This is very interesting example, Steve. Yes. So, and also, as you can see here, in the step response, now we see like a very big spike, right? So earlier we used to see a spike in the earlier result, right? We saw a spike in the below plot, which is the impulse response, but not in the other two plots. But now we see the spike in the other two plots, right? So this, what it means is it is not a change of cable type. This is a big discontinuity in the shield, and that's what you just described, is that maybe there is only little bit of shield is left, or somehow earlier we discussed, right? Somehow if the component is actually unshielded, but there is a AC continuity, you see something like this, which is very, very evident that this is a problem that needs to be fixed.
Right. So in the real world, if this cable was in a normal commercial building cabling system and the cable had damage like this, what could happen is excessive noise from a wide variety of sources could get into this cable and cause problems with it. Great troubleshooting tool. This could also happen during installation if, depending on the environment, where it was being installed, if something got hung up on the cable and the cable somehow got damaged during the installation and it compromised the sheath and the shield, you could see something like this. Now, normally, following typical guidelines, you're not going to see that kind of damage in installation. Something like this, in most cases, would be after the fact. Something happened to the cable later on after it was installed. But another example might be a shield that wasn't terminated properly on the connector at one end or the other of the cable, and that would show up as a large impedance spike as well, correct?
Absolutely, yes.
Right. So this is the kind of thing that that's going to give the installer the ability to troubleshoot and figure out, okay, yeah, I've got a little alert here. My shield has a problem, but how do I find that problem? And here you can see we click on that spike, and we can see that clearly the distance to that event.
Mm-hmm.
So there are some testers out there that will also do a shield test like this, but they only show you that wire map in the beginning with the indication on the wire map of the open and where along the cable that open happens to be. They, in many cases, they won't show you the level that we're showing you here, where you see this TDR trace with that discontinuity issue along the cable. And you can even zoom in on these. So if you wanted to pinpoint where that spike starts, you can zoom in on the results, and you can go ahead and pinpoint the that point where it takes that spike, where you see that open. And these can be isolated. So if we just want to look at it just from the main end with the step TDR, we can see that. Or if we just wanted to look at it from the remote end with the step TDR, we can do that. Or if all you want to see is the impulse TDR that Harshang mentioned, we can just look at the impulse trace and see that. Now, there are some spikes at the beginning and the end here. Would you like to talk to those, Harshang, at all?
Yes. So these spikes are mainly due to the connector going into the patch panel, right? So the first connector and the second connector, and the impulse response always shows any amount of discontinuity, right? But so both types of plots have their own utility. The impulse response is very good at showing the discontinuity, whereas the step response that we have is able to show the permanent changes in impedance. So,
Gotcha.
so the combination of the two gives you a very complete view of what type of issues we are looking at.
Right. And it's good to have the ability to see this from the main and the remote as well when it comes to step TDR, correct?
Correct. That's why the tester shows two types of TDR plots, one taken from the main end and the remote end. So it helps to look from both ends. And I think from the remote also you can view both plots.
Yes, I can touch my I can go to my remote here that we've got, just so everyone knows. The main is the screen you're seeing here, and then I'm going to my remote, and I'm going to scroll down to this same trace, and I can see that same trace on my remote now.
Mm-hmm.
So we can see that, and it's presented relative to each end. So if in this case, it's a spike halfway through the cable, but if it was closer to the remote end, you'd actually see that on the trace on the remote. It would show that the event is closer to the remote rather than being closer to the main.
Correct.
So that's another benefit of having the dual end display like we have with the TestPro. The other thing, you probably noticed when we plug these testers in, we immediately get the wire map. So if we do have a wire map problem, we know about it right away. But in the cases that we're discussing here, we're showing you some examples of where that initial wire map might look good. That shield continuity looks okay. But when you run the test, it's alerting you. It's telling you, hey, there is an issue. You've got something going on with the shield. When we look back at the wire map, we can see we've got something going on at the shield. There's a little bit of something happening at my near end here. There's something that's halfway through the cable. So we're seeing an indication, and this will show up whether it's a partial open like we've seen with that midpoint spike that we saw, or it's a change in the cabling type. So you can get a pass test like we saw earlier that will still have on the wire map, it'll show you some indication of something going on with the shield here. So in that case, it's telling you everything looks good, but we want you to take a look at the shield because there is some discontinuity in the shield type. Now, Harshang, if there is a discontinuity in the shield type along the cable, what impact does that have to the system being able to operate the network being able to operate properly if the shielding has some kind of changes in the shielding along the channel.
So in many cases, Steve, I think there may not be like a direct impact in the network operation, except when you have network upgrades. So for example, you have an FTP cable in the middle of an SSTP channel, and that may just be fine for the regular operation, and it may even pass the limits. But if along the way, if you increase the data rates, or if you have the noise sources that come in the play, right, external noise sources, then you may start having problems, particularly at the connection points, because the cable itself, either it is FTP or SSTP, I mean, in both cases, it is very well protected against noise. But at the connection points, if there is a transition from one type to other type, you have some weaknesses. So I think it is not a good practice to have mix and match of different cabling types in a single channel. Right? It is ultimately, we have shield because we want to see the cable having very high noise immunity, and by having such mix and match, uh, all the effort that we put into ensure this immunity get compromised. So why do that?
Gotcha. That makes sense. And that's kind of this spike we're seeing at the beginning here. Because remember, when I
Yeah,
set this test up, I have a permanent link adapter, but I'm actually connecting it to the other end of this long shielded patch cord that's been compromised, and I'm going through a coupler. So that's this spike we're seeing in the beginning here, and this may be that connection point where you mentioned where if the shielding type changes at the
yeah,
connection point is where you might have a problem. So in a cable like
correct.
this, if I was using this scenario, I would suspect that if I'm going to experience noise problems, it's going to be because of this connection right here.
Yes. So Steve, I believe the cable you have, cable under test, is an FTP cable with uh, a single shield around the 4 pairs.
Ah,
Whereas,
okay.
right, whereas the permanent link cord that comes with the tester, the permanent link cord is a SSTP cable, right? So it has a shield around every pad, and then there is an overall shield.
Gotcha. A significant difference in the shield coverage.
Right, right. So that's why you see these steps in the step TDR.
Okay, gotcha. So it's not abnormal to see a step like that, to see a jump like that in the step TDR trace because of the fact that not every cable that you're installing is going to be the same as what's on your permanent link adapter.
Correct, correct. So it is, yes, that's a very good point, Steve. So we should not be alarmed if we see a single step at the end of the permanent link adapter. But if you see another step along the length of the cable, that indicates some trouble, right? So there some mismatch that you didn't want to happen.
Gotcha. Okay. And then if you're doing a channel test, then the recommendation is going to be that the patch cords that are part of the channel test you'd want those ideally to be the same shielding type as the installed cabling, correct?
Ideally, yes, Steve, but in many cases, you will have the situation like what you have at your setup, right?
Right.
So as long as you are getting what your system is like, I think that is fine, right? But sometimes, I mean, we may be thinking that it's all same type of shield, and if we see a step, then we should be worried that it is not what we thought it is.
Right. It's not necessarily that there's a step, it's the intensity of the step, correct?
That is another point. Yes, very good point, Steve. Yes,
Yep.
it is the intensity of the step. So in this case, it is jumping, but jumping by like 4 ohms. And
Right.
and by the way, the y-axis here is
Mhm.
is in ohms, right?
Right.
So you are actually seeing the impedance, and that's what TestPro does. Very unique because unlike in the differential signal that I was mentioning earlier, the regular measurement of return loss or insertion loss, we have 100 ohm differential pair. But when we treat the pair as a single wire, right? By applying the same voltage in common mode. The uh, the the meaning of impedance takes a different meaning. I mean, basically, we are now talking as if we are treating a coaxial cable with center conductor and the shield.
Right.
So yeah, so this is why you see like a 25 ohm as a reference impedance as against 100 ohm in the differential signals.
Gotcha. And I think this also points out, you mentioned about the step TDR, these upper traces here, they actually represent measurements at many more data points than the typical impulse TDR. Therefore, they can find problems that might be overlooked by a typical impulse TDR. And you can see here a difference in the trace. The impulse TDR, while it shows us a spike here that we know shouldn't be there, you can't really gauge the intensity of it until you look at these step TDR traces, right?
Yeah, so step TDR traces, that is one thing, Steve. Step TDR traces are showing the problems more evidently, but also there is another thing. So for example, right, if you have a problem in the shield in the middle like you have now, then if the cable at both sides is same type, then what will happen is the regular trace on the right side of the spike and the left side of the spike will have pretty much the same reference level. But if the cable changes permanently, you will have like a big step. So after the spike, you will see like the whole level is raised.
Like this example right here.
Like this example there. Actually, that rise is in fact not so big. I mean, if you look at the initial change, right, the one where your cursor is,
Mm-hmm.
you are seeing that there is a change and that change is permanent, right?
Right.
Whereas after the spike, uh, because the spike is so big, you are still seeing some change. But if you look at that other plot, right, the yellow plot,
Yep.
you see that before and after the spike, I mean, if you just remove the spike, it would look like a straight line almost,
Yeah.
right? Right. So that kind of indicates that the cable types on both sides are similar or not so different.
Right.
Okay. But the problem is the rodent thing you mentioned.
Yeah. Yep.
Right?
Causing changes in the cabling
Yeah.
itself and
Yeah.
compromising that shield. So
Yes. Yeah.
I'm going to stop sharing my screen now and just go back on camera here. And let me pull this up because I think we're getting close to the end here. So I'm going to see if we have any questions. We've got a comment here from Hadley Stevens. Thank you. Extremely educational. Appreciate the comments there. Don't see that we've got any questions. I know I addressed some of the questions in the beginning. And one question that we did get that I actually had come in from somebody last week that I thought would be good to bring up today is they specifically wanted to know, when I'm installing a shielded cable, do I have to bond it at the patch panel and at the faceplate? And their question was about ground loops. And of course, the answer in a permanent link cabling situation like this is it's you're bonding the shield of the cable to the connectors that you're terminating. So you're using shielded connectors at each end, and then the shielded connectors in the panel are actually bonded to the rack and to the building ground system through bonding and a bus bar and ground wire. They go off to the building ground system. So you've got the ground at that end, and then at the far end, assuming you use a shielded patch cord, which you should, then you're grounded when you plug into your equipment, your PC or whatever you're plugging into at that end, because that's going to be grounded through the electrical system.
Mm-hmm.
And with a ground loop, can you explain a little bit, Harshang, about what happens if you have a ground loop? What happens to the noise?
Yeah. So the noise immunity degrades if you have a ground loop, right? Because the ground loop acts like an antenna by itself, which means that it can send and receive signals, which we don't want to happen, right, with the outside world. So like you just mentioned, if you have another bonding to the ground at the connection point where your device is or equipment is being connected, that is a bad idea, right? Because equipment, like you mentioned, is already connected to ground. You don't want an additional connection to ground at that point.
Right. And you could create the same antenna issue if you use an unshielded cable to go from your computer, for example, into that wall plate where you've got a shielded cable running back to the panel, because now your shield is only bonded at one end. So now you have an antenna, correct?
Exactly. Yes. Yes.
Yep. So great. Well, fantastic. I see we're right at our 30-minute mark, Harshang. I really appreciate you getting on. For those of you that don't know, this is the middle of the night for Harshang. So we greatly appreciate you joining us, Harshang. I know it's bedtime or past your bedtime, but we really appreciate it whenever you can join us, and you always lend a lot of good information to the episode. So we greatly appreciate it.
My pleasure, Steve, and thank you so much for having me.
Okay, and we'll see everybody again in 2 weeks on the next episode of Tech Talk with Steve. Thanks for your time.